Okay, so today there's a lot of concepts I want to show you. Well, it's actually one concept, but I want to show you some examples before we head into the exercises. So I was talking to my husband this morning, and he and I both had the same experience in high school where they did not explain L'Hopital's rule. They said, this is how you do it. And we did it dutifully, and it wasn't until much later that we actually understood why it worked. And it's a beautiful thing, and the concepts are really beautiful. This dude, L'Hopital, is French, and his name is not hospitals. A lot of students mispronounce it, but technically it does translate to hospital, but please call him L'Hopital. Anyway, so there's that. I want to talk about what it means when you do a limit as x goes to whatever. It doesn't really matter what. And let's say you have 0 over 0. Okay, like the thing on the top goes to 0 and the thing on the bottom goes to 0. That's the situation that we are dealing with. I want to explain it conceptually and then explain algebraically, and then there's all sorts of variations. This is called indeterminate. The big deal is you were probably told 0 divided by 0 is undefined. And today I want you to say requires further investigation. Okay, so I want you to just sort of turn that whole idea upside down. But the other things you were taught, these ones are still cool. 0 divided by a quantity is 0, quantity other than 0, some number. Some number divided by 0, you can still assume that's infinity. That's all cool. It's just this 0 divided by 0 case, and there's all sorts of other cases like infinity divided by infinity, infinity times 0, and there's ones with exponents in it, and all the rest of it. Okay? So this is just going to be a whole big ball of wax here. Now, for me personally, everything makes way more sense when it's graphed, or sometimes in my mind's eye. I can't really show you graphs going out to infinity. You're going to have to imagine those. And I'm going to give you some graphs that are in the zone where you can see and imagine more easily. So let me start with a really simple one. Say 3x versus 4x. And those both, let's say I'm limiting as I go to 0. And I'm looking at those two lines, and the two lines are forever lines. They're lines everywhere, and I can zoom in and zoom out, and they'll look the same. So I can just go ahead and zoom in for you, and it doesn't make any difference at all. It looks really exactly the same because they are these lines after all. And so what we're saying is no matter how far you zoom in, they're still going to be in a certain ratio as you get to 0. Okay, so for example, I'm going to look at this, let's see if I can put this point here, for example, versus the point directly below it. That's in some ratio. And as you zoom in, that ratio is maintained. So even though eventually you're going to land on 0 and it's going to explode, we're not allowing you to land on 0. We're saying, what is the ratio of the slopes of these two lines as we go into 0, and that ratio, depending on which one you put on top, is either 0.75 or 1.33, okay, depending on how you stack them. But it's clear that these guys are actually coming in as two lines. That is the base case, and that is the ideal optimal case you're kind of thinking of in a way. And then there's the other cases where you end up with you're going to essentially explode to infinity or go to 0 based on which way you stack them. Because if one of them is coming in completely flat and one of them is coming in at an angle, then you have a different situation. Okay, this time I'm going to do something very similar, but I want to just explore natural log of x where it hits 0. And this is actually the same as just asking about a tangent line, really. I just want to see if, I just want to zoom in there and see what that slope looks like. So rather than zooming in right there, it's just easier for me to shift that graph over just so that it's easier for me to create a tangent line. I don't have to worry about adding in an intercept. So I'm just going to put in a +1 here so I can slide that guy over. There we go. Now he's right at that 0 is right at the origin. It's just going to make it way easier for me to zoom in and see what's going on and come up with a hunch. So I'm going to try to zoom in And as you can see, it looks like we're straightening it out to a slope of 1. And as I zoom in, that becomes more and more obvious. And you see, as I zoom in, that looks more and more like a line. At this point, I am pretty convinced that this is the right thing to be doing. And I'm going to try y equals x as my line, and there I go. When I put in the y equals x, it completely coincides with natural log of x plus 1. That is a numerical demonstration that if we're not right, we're really, really, really close. Okay, so that's not proof, but the calculus will bear us out. Okay, but this is just the numerical demonstration that if we're not right, we're really, really close to what we're trying to do. All right, next example. Okay, in this case, I have an x squared and an x to the 4th, and it looks like maybe we have this guy, this blue function. It doesn't look like it's really the same kind of shape as the parabola. So in fact, what's happening is the blue curve, the x to the 4th, is coming down for a landing, in a sense, much faster than the red curve. It's coming into 0 much more at a much shallower angle, I guess, so that the red curve, the parabola, is coming in more at, a steeper angle. And so the question is, as we zoom in, what is the relative size? What are the relative sizes of these guys? And you can just on Desmos. I have a touch screen. This makes it really easy to zoom in. And the point is, you don't want to zoom in too close to 0. This is a whole sense of scale. If we zoom in too close to 0, then those two curves appear to overlap. And if we go too far out, then they look too curvy, and they don't look like they're coming in at exactly like a same ratio. You need to zoom out to a place where you need to sort of do this. This is what calculus gets you. Okay, this calculus gets you being able to do this. You need to see where neither one of them is 0, but they kind of both look like a line. I'm going to find a place. It takes a while to find a sweet spot. Okay, basically I give up. Okay, so the point is that x squared, even though it's coming in here, we find that we're really, really close to 0, super close to 0. The blue curve, the x to the 4th, has us beat. Right? So if as we're coming in close to 0, if we say like x squared over x to the 4th, it's going to be like divided by 0. Even though it's 0 over 0, it's like really like a number divided by 0, because no matter how close you get, when you get zoomed in here, it really looks like the red curve is much higher than the blue curve. And for that reason, if you say x squared over x to the 4th, the x to the 4th gets to 0 first. And if you say x to the 4th over x squared, then you have the opposite effect. So let me just explain that in writing here. So if we say the limit as x approaches 0 of x to the 4th over x squared, this guy essentially goes to 0 first, and this guy has some value not equal to 0 relative to x to the 4th. So this whole limit is going to be 0. And if you flip that around, why then, of course, the thing that's 0 is essentially on the bottom, and division by 0 is going to be undefined, and you are going to get yourself going off to infinity. So it's a matter of who gets to 0 first. And remember, we never arrive at x equals 0. The whole idea of limits is what is happening in the nearby vicinity if you just disregard that actual point. We want to know what's happening in the nearby neighborhood. Okay, so this might have been the one I was thinking of. Like, it's really a lot easier to sort of zoom in on these guys. And you would think that x squared and x to the 2.2 is very, very similar, and they are. So this one is a little easier to zoom in on. And you can see as you zoom in that these appear to have some kind of relative size, but you'd be mistaken. Okay, this is sort of a trick of the eye, because the change happens so slowly. This is actually the same situation we just had before. The blue curve still beats out the red curve in getting to 0 faster, and so relatively speaking, the red curve has some positive value and the blue curve is 0 essentially. So if you do red over blue, limit as you go to 0 is still going to be infinity, but if you put the blue one on top over the red one, the limit is going to be 0 as you go to infinity. So that's a fun one to look at. Okay, this one is sine of x versus x, but before we sort of give that away, I mean, that is going to be what we end up choosing as our tangent line there. Let's just zoom in like we did with the natural log until we're pretty sure that that's what we're dealing with. And then I'm going to put the x curve in here, and you can see that it is numerically plausible that that is the correct value. And in fact, it is. Okay, so square root of x is, look what is happening to it at 0. That's lovely, but there's a problem there because if you zoom in, you'll find out, actually, if you realize it's just the parabola anyway, you know that x squared has a derivative of 0 at 0, so you should not be surprised to find out that this has an infinite derivative. It's just not, this just goes straight up. This is a function that's often used to demonstrate problems at 0. Okay, so what are we going to do? I'm going to actually just slide it over like I slid over the other curve. And I just want to deal with a different point on this same curve. There we go. Okay, so let's just now knock that down a little bit because I just want to deal with another 0. Okay, so I'm just looking, I've just shifted the curve around so that I can easily create a tangent line here, and I'm trying to figure out what it is. Clearly it's not y equals x, but it looks like it might be y equals x over 2, for example. So I can just explore that and say, you know, that's kind of plausible, and the further I zoom in, the more certain I am that I guessed right. Okay, so if you guess wrong and you zoom in, then you will find that those are not working for you. That ends up being the correct guess. Okay, so that's the end of those demos, but I want you to see Desmos as a tool that you can use to help explore your understanding of tangent lines and L'Hopital's rule, and hopefully the tangent lines and the L'Hopital's rule go hand in hand for you, and yet there's a lot we need to talk about that is algebraic. So I don't want you to neglect the concepts just because there's a whole bunch of little algebra rules you need to learn to get through the exercises here. Okay, so now we're going to start talking about some of the rules you need, some of the algebra tricks you need. So for example, problem 1, what kind of algebra tricks do you need? So these essentially, I think of them as two flavors. One is just pure algebra tricks, and then the other one is taking the derivative. So usually when you learn L'Hopital's rule, you just learn like when are you allowed to take the derivative of the top and the bottom. But what is the derivative? That is the slope of the tangent line, right? So what you're really going for is you want to know what is the slope of the tangent line. And that's why we do this whole thing of zooming in and trying to find what is the tangent line at that point, because we are trying to find the slope of the tangent line. That means we're trying to take the derivative. Okay, so you can always just take the derivative, but there's also algebraic stunts. So let me give you an example of an algebraic trick. Okay, if you have something that factors in the denominator, you can go ahead and factor it, and if it just so happens to cancel with something in the numerator, then that's fine, provided you're not letting x equal -1, but you never are in a limit. Like the things that cancel are always integer roots, and the thing you're going to is always an integer, and you're never going to get there. So this is never a problem in this type of exercise. So if you see something that cancels, go ahead and do that. And the other big trick is you can take the derivative of the top and the bottom. So for example, if you have a problem like this, limit, let's say you didn't notice that that canceled, x is going to -1, and you say, whoa, 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 that's 0 over 0. That gives you L'Hopital's rules, privileges, and I just sort of notate that to remind myself of how I did this, because sometimes I just forget what gave me the right to do that, and I'm like, oh, right, that was 0 over 0, take the derivative of the top and the bottom, and then you end up with, okay, now you can just plug in that -1 in, and then you get -1/2. Okay, but what would have happened if we would have used the canceling trick? We could have done that thing that I showed you, the canceling of the algebra, and then you would have used 1 over x minus 1, and let's see, it would have been -1 minus 1, and we would have gotten -1 over 2, which is the same thing. So the math works. Either way, there's often more than one way to reach the same correct answer. Okay, little warning on question 1C. You're going to have to use repeated L'Hopital's rule because this is a situation where you have infinity over infinity, and that's another L'Hopital's rule, and you're going to take the derivative of the top and the bottom. You're going to still end up with infinity over infinity, I'm afraid, and then you're going to have to use L'Hopital's rule again. Eventually, you're going to get out of the woods and you'll get to something you recognize. So don't be discouraged, because that is as intended, and that is a situation where rather than 0 over 0, it's infinity over infinity. All the same concepts apply. 0 over 0 versus infinity over infinity, but just imagine like this is going infinite and you're going to infinity, and you want to see which size of infinity is bigger, and it's all the same concepts as going to 0. So I want you to, in your mind, sort of figure out why 0 over 0 is actually the same case as infinity over infinity. One little mental trick to help you is if you're thinking 0 over 0, what's 0? Well, 0 is kind of like 1 over infinity, so that actually makes some amount of sense, because then it's like, wait, 1 over infinity times flip and multiply is just going to give you infinity over infinity, and the same argument can be run backwards to show you why infinity over infinity is the same as 0 over 0. But to be honest, I can't visualize infinity over infinity anywhere near as well as I can visualize 0 over 0. So there you go. Okay, these problems are good for you to explore numerically. Problem 2 is, I want you to think about that. I want you to plot these on Desmos and try to see if you can get like a gut feeling for why this works the way it does. But some rules is if you have two polynomials, like a polynomial that has leading term is x to the 4th, and a different polynomial whose leading term is x to the 5th, let's say, then this polynomial with x to the 5th is going to essentially reach infinity faster, and this guy is going to look slow in comparison. And it actually doesn't matter what the coefficient is in front. It doesn't matter what its friends are, like it's x cubed and x squared friends. It doesn't matter. You just look at the leading term of that polynomial, and the only thing that you really have to focus in on is what is that power, because regardless of the coefficient can only take you so far before the exponent is actually the more important part of the system that you're dealing with. So just kind of be aware of that polynomial thing. Okay, and the other things you will want to know is things like, okay, so you have polynomials here, and within the polynomials you have like lines and like a constant, and then you have a line, parabolas, cubics, and so on and so forth. So they're kind of a family, but they have a hierarchy inside. But then you have things like e to the x that are faster than polynomials, and there's actually things faster than e to the x. But you have things like, say, 3 to the x is faster than e to the x, or like 2 to the x is slower than e to the x. So these things to the x, you can think of them as being a family if you like, but they're dramatically faster than each other. Like the drama in this family is much more pronounced than the drama in the polynomial family. You also have like the natural logs that go really, really slowly to infinity. And so that's sort of in your mind. Just think of natural logs as the slowest, polynomials as kind of in the middle, and exponential functions are faster than that. And that's a good set of conceptual rules of thumb to get you through this question. And then what you should do is either use L'Hopital's rule or some kind of graphics to help you verify that you've got that right. Okay, so the bit I want to sort of tell you about this problem it's kind of hard to draw straight lines. Okay, so there's a curve like this that you can basically assume that when you zoom in it's a parabola. It's not a perfect parabola, but you assume that as you zoom in, it behaves as one. And so this is g of x down here and f of x up here, and you can basically assume that they're more or less mirror image of each other. And so hopefully that's enough of a clue to get you through that. So you should be aware that, okay, so they share the same 0. And let's see, f prime is going to be negative because you're going down, and then it's going to turn around and be positive, right? That's what f prime does. And then it's concave up. So f double prime is going to be positive, and the reverse here. So g prime is positive and then negative, like before or after the 0. And you know it's concave down. So its second derivative is always going to be negative. And that should be enough information to get you through this question. Of course, remembering L'Hopital's rule, since it's a 0 over 0 situation, you're going to have to take the derivative of the top and bottom. You're going to still get 0 over 0, and so then you're going to have to take the derivative of the top and bottom a second time. So it's a repeated L'Hopital's rule, but it's all visual. This is a visual 2 times L'Hopital's rule. And again, the question's only asking you to understand the sign of the expression SIGN, and it's not asking you for a numerical answer. Okay, question 4 is just sort of introducing you to a sneaky little trick that you can use that you might not have realized you can use. So f of t is equal to some kind of mess. I'm just going to put down here mess because you'll have to deal with it. And it's to the 1 over t. And so you're like, oh my gosh, I'm going to take a limit as t goes to 0, for example. I'm going to take a limit as t goes to infinity, as t goes to negative infinity. I'm going to do all sorts of nasty stuff. But I'm kind of nervous because of that exponent. And so what I'm going to do is I'm going to take the natural log of f of t, and that's going to allow me to take the natural log of everything on the right-hand side. So I get to natural log of mess. I'm sorry, I did this wrong. 1 over t times natural log of mess. So this structure allows you to pop that 1 over t in front of your natural log. And then what we're going to do is we're going to say, well, I'm going to take the limit of both sides. Limit of junk equals limit of junk as t goes to wherever you want. You're still going to wherever you need to go. So this lovely garbage goes over here. But then when you're done, you're going to have to untransform it. Okay, so if you want to know what the actual limit was, you have to reverse engineer that. And so let me give you a brief example with the concrete values you might know. Let's say I have limit as t goes to 5 of t to the power of 1 over t. That's actually just going to be 5 to the 1/5, and you can just put that in a calculator. So that's not really a mystery. But let's say you didn't realize that and you sort of went about this like really the long way. So maybe you said, oh no, let me take the natural log of this whole mess. And later I'm going to say e to the power of all that stuff to figure out what my answer was. So I'm going to say like t to the 1 over t, but because I just put this natural log here, then that should allow me to put this thing out somewhere, but I can't put it outside the limit. But strangely enough, I should be able to put the limit outside the natural log. So t goes to 5 of 1 over t natural log of t. Let me see if I got that right. Okay, so now I'm just going to say, well, this is equal to 1/5 natural log of 5, but that's not the answer. Remember, the whole answer is 5 to the 1/5, and we kind of forgot that. We didn't do it the easy way. We did this crazy thing. Now we're going to say, okay, at least we have our limit. Now we had taken the natural log. What's the opposite of natural log? So now we're going to go back to the opposite of natural log, e to the power of all this mess, and then we're going to say, well, what's that? E to the natural log of 5 to the 1/5, and so the answer is 5 to the 1/5. Okay, so we really took the long way around to do it. But I just wanted to demonstrate that when you put a natural log and a limit together, there are some rules about when you can do this, but given that nothing really weird is happening and you're not hitting 0 in a weird way, then you are allowed to invert the order of the natural log and the limit Okay, when everything is nice, you're allowed to do that. And then that sometimes just makes the algebra come out nicer, and it helps you get out of a mess you are in. So again, it's an algebra trick. It doesn't work when you hit certain cases where things are exploding. But if things are relatively nice, this helps you work through your algebra issues. Okay, so the couple things about question 5. There's this thing arc cosine of x, and the whole problem is in the context of 1. X is 1 from the negative. But I just want you to realize that you don't always have to use algebra. Sometimes you can do this stuff visually. And remember that what cosine looks like was like this, right? And so what is arc cosine? Well, you're going to take this piece from here to here and you're going to flip it, right? You're going to flip it so that what? So that you have, going to flip it here. That's roughly where y equals x is. And you're going to flip that around and, okay, so it looks something like this. So if cosine has a 0.01, arc cosine is a 0.10, and this point is analogous to this point over here. So the point, it's at pi 0 becomes, pi negative 1 becomes negative 1 pi. So pi is up there. This guy should be at pi over 2. This guy is at 0. So this is flat here because you know it's a cosine curve, which is the same as a sine curve. And when it's flat, it's flat. So you know that derivative is infinite. Okay, so if this helps you get out of that jam, then you don't have to actually go through with taking a derivative. You can just sort of figure out what the derivative should be graphically and then put it into your mental calculations. Because the other alternative is just go out and look up the derivative of arc cosine, which is a major pain. Like you'd have to go to Wolfram alpha because derivative arc cosine is just nasty. Fine, arc cosine of x, whatever. But you really don't want to deal with it. I mean, you can if you want, there it is. But it's just easier ways to deal with it. Just think about it conceptually rather than with a whole bunch of nasty algebra. Okay, so this one, the part 5b, question 5b, this expression e to the t minus t to the n. Just to explain what that is. E is e, t is your variable, and n is any positive integer you pick. You can pick 100, you can pick 1,000, you can pick 1,000,000, you can make it as big as you want, but once you pick it, it's there. And the question is, for 5b, does it actually matter how big n is? And if you heard the first part of this video, you probably are already saying, no, it doesn't, because the e is going to win anyway. And that's pretty much the point of this exercise, is to drill that in, have you just think about it a little bit. So it looks like some kind of indeterminate form because it's infinity minus infinity, because if you just took this piece and you went to infinity, you get infinity, and this piece and you go to infinity, you get infinity. But those two sizes of infinity are very different. It's like big infinity minus a measly little infinity. So the big infinity is going to win that one. And so I just kind of gave that one away. But thanks for listening. And I think there might be another question. But you guys are going to have to figure it out, think about it, and then ask me if you get stuck. All right, see you soon.